Last time we talked about tests for sufficient conditions and necessary conditions. And those tests will work fine in a lot of cases, but they're not going to work in all cases. Because remember, we were looking at what caused death. Death, well, you're either dead or you're not dead. And we talked about whether the person had fish or not. We didn't look at cases where people ate just a little bit of fish. They either ate fish or they didn't eat fish. But there are a lot of causal relations that hold not between absolute or dichotomous properties, you're either dead or not dead, you ate fish or you didn't eat fish. Instead, some causal relations hold between properties that come in degrees. For example, carbon dioxide and global warming. Well, there's always carbon dioxide. The atmosphere always has some of it. So you can't say that carbon dioxide is sufficient for causing heating in the world, since sometimes the world cools down and there's still some carbon dioxide then. So what we need to think about is the degree of carbon dioxide. And sure enough, that's what the Intergovernmental Panel on Climate Change, the IPCC, used to reach its conclusion that increasing levels of carbon dioxide were causing increasing global temperatures. And we can't use the sufficient condition test or the necessary condition test, but we can still reach a conclusion about causation, and we can even know the mechanism for the causation. The carbon dioxide reflects the heat from the sun back to the earth and traps it in like a greenhouse effect, as it's called. So the question for this lecture is, how are we going to use arguments to justify those kinds of causal claims? So let's look at another example. Suppose a runner runs a mile and it takes them 10 minutes. Why were they so slow? Well, maybe because they were really heavy. Now, weight can't be sufficient for running slow because everybody's got a certain weight. So it's not an on-off property. It's a property that comes in degrees. And again, the heavier, the harder it's going to be to run. We know the mechanism because it takes more energy to move a heavy body. So we've got a pretty good causal story and a pretty good causal hypothesis, but you can't use the necessary and sufficient condition test because we're dealing with properties that come in degrees. A third example, suppose the wages go down. Well, that's because the unemployment was high. There's always some unemployment. Wages are never as high as you'd like them to be. So how do you get a causal claim? Well, it's because the more unemployment there is, the lower the wages are, because if a lot of people are unemployed, they're willing to take jobs for a lot less wage. So we've got a causal story, we've got a causal claim. They seem to be justified, but you can't use the necessary and sufficient condition test. You need a different test. And the test you need has to deal with properties that come in degrees. And the test that does that is called the method of concomitant variation. It was developed by John Stuart Mill in the 19th century. Brilliant philosopher. He also developed tests that basically what we've been calling the necessary condition test and the sufficient condition test parallel. He gave them different names, but it's the same basic idea. This lecture's on the method of concomitant or concomitant variation, also developed by John Stuart Mill in the 19th century. Now, in order to apply the method of concomitant or concomitant variation, the first thing we got to get straight is the idea of what a concomitant or concomitant variation is. Well, to avoid that word, people these days call them correlations. And the first kind of correlation we got to understand is a positive correlation. X and Y are positively correlated when an increase in X is associated with an increase in Y, and a decrease in X is associated with a decrease in Y. That's what a positive correlation is. In contrast, a negative correlation is when an increase in X is associated with a decrease in Y, and a decrease in X is associated with an increase in Y. That's why they're negatively correlated, because increase is associated with decrease. Whereas they're positively correlated when increase and increase are associated and decrease are associated. So let's look at some examples. First of all, calorie intake is associated with weight. The more calories you take in, the more weight you're going to gain. So they're positively correlated. Whereas weight and exercise are negatively correlated. The more exercise, the less weight, because it burns off those calories you took in. So you get a negative correlation between weight and exercise and a positive correlation between weight and calorie intake. Another example, height and age are positively correlated before the age of 20 because people tend to get taller as they grow older. But height and age are negatively correlated after the age of 60 because the space between people's vertebrae tend to decrease after a certain age. So this shows that two things can be positively correlated in some circumstances and negatively correlated in others. Which correlation holds is going to depend on the circumstances, that is, how old the person is. And now the next question is, how can we get from these correlations to causal relations? When two features are correlated, positively or negatively, then there are four possible causal relations between them. First, A might cause B. Sometimes when A and B are correlated, that means that A is causing some kind of change in B. Second possibility is that B causes A, because the correlation is symmetrical. If A is correlated with B, B is correlated with A. And then we don't know whether A causes B or B causes A. But those are two different possibilities, and we'll have to see how to distinguish them in a minute. But the third possibility is that some third thing, C, causes both A and B. If C causes B and C also causes A, then A and B are going to be correlated. Because whenever C is there, you get both of them, and when C is not there, unless something else causes them, then they're not going to be there. So A and B will be correlated simply because a third thing, C, is causing them both. And the fourth possibility is that the correlation is purely accidental. A and B just happen to change together. Okay? So here are some examples. First of all, let's do an example of A causing B. Okay? The speed of driving is positively correlated with automobile accidents and deaths from automobile accidents, because when you're going very quickly in your car and have an accident, you're more likely to die. Okay, which causes which? It's the speed that causes the accidents and the deaths. The death didn't cause you to drive faster before you died. That seems pretty clear. Okay? Now what about the second possibility? B causes A. Well, it's just the reverse. You can use the same examples. You can say automobile accidents and deaths are correlated with fast driving, with speed. And in that case, it's not that the thing we mentioned first causes the thing we mentioned second. It's the other way around. Because as we said before, it's the speed that causes the automobile accidents and the deaths, not the deaths and the accidents that cause the speed. Okay? What about the third possibility? That some third thing causes them both. Well, here's an example. Having yellowed teeth is correlated with having lung cancer. Well, why is that? Because there's some third thing that causes people's teeth to become yellow and also causes lung cancer, namely smoking. So people who smoke tend to have yellower teeth, and they also tend to have more lung cancer. So those are correlated because smoking causes both of them. Okay? Another example. In young children, shoe size is correlated with the quality of handwriting. As people's shoes get bigger, their handwriting gets better. Now, why is that? It's because they're maturing. And as their bodies mature, their feet get bigger, and also their handwriting gets better. So now we have an example of each of the first three types of cases that we talked about. What about the fourth? Correlation is accidental. Well, here's an example. The height of my son and the height of the tree outside the window, well, they're correlated. The taller my son gets, the taller the tree gets. And the taller the tree gets, the taller my son gets. They're symmetrical. They're correlated together. But does that mean that something about the height of my son causes the height of the tree? No. Or vice versa? No. Well, you might say there's some third cause, namely maturation. But unlike the case of handwriting and size of feet, where it was the maturation of the same person, the same body, here my son's body maturing and the tree's body maturing are just unrelated. You might say that time is the third cause that makes my son grow and also makes the tree grow. But notice that time is an abstract thing that's always there and always moves at the same rate. So it can't really cause my son to grow at this particular moment or the tree to grow at this particular moment. It's a background condition rather than a cause in and of itself. So now we've got 4 possibilities and we've got examples of each. The question that we have to face is, fine, all 4 are possible. How do you tell which of these possibilities is the one that applies in a particular case? That's going to be tricky. So the problem is, how can we tell which of the 4 possibilities applies in a particular case? And one simple rule is that when A causes B, A has to come before B. So if the first possibility is instantiated, then you have to have A coming before B. But if the second possibility is instantiated, then you have to have B coming before A. Now, in the last 2, you can have them on any temporal relation you want. But if A comes before B, then you know that B doesn't cause A. And if B comes before A, then you know that A doesn't cause B. So, for example, exercise is correlated with weight loss. Could it be that the weight loss causes the exercise? Well, it's possible, I suppose, but if the exercise occurs before the weight loss, then we know that it's the exercise that causes the weight loss because the exercise occurs before the weight loss occurs. And we can use that temporal relation to decide what causes what, at least in some cases, because sometimes when you're dealing with a constant factor like CO2 variations or pollution variations over a long period of time, and if pollution causes acid rain, you don't know exactly which part of the pollution is causing which part of the acid rain, and the parts are occurring over a long period of time. So you can't tell which comes first. But at least in cases where you can, like the exercise and the weight loss, then you can say which causes which. Now when they're not in temporal order like that, you have to use a different method. The second method of determining what causes what is manipulation. This method is used in a lot of scientific experiments where they manipulate one factor to see whether that factor causes something else. When you do those types of experiments, you have to make a lot of assumptions or test a lot of background conditions to make sure that there's no independent factor that's causing the effect. But in the right circumstances, it can work. If you want more detail about which circumstances need to be met, then there are books by Woodward and by Pearl that spell this out in great detail. But here, we're not going to go into any great detail. We're just going to give you the basic idea. And the basic idea is that you manipulate A and then look to see whether B changes according to the change in A. And you manipulate B and look to see whether A changes in accordance with the change in B. And that's going to help you determine what causes what. Because if when you manipulate A, B changes, then that's an indication that A causes B. Because if B caused A, then manipulating A wouldn't have an effect on B. Think about it this way. You put the wood into the engine of a steam train, and the wood affects the motion of the train because it affects the way the engine works. And then the train produces steam. But the steam doesn't cause the train to move, it's caused by the train. So if you manipulate the steam, like with wind blowing the steam around, that's not going to change the train. So, similarly, if you change A and B changes, but you change B and A doesn't change, then that's a pretty good indication that A causes B. And that's going to rule out the second one, right? That can't be true if A causes B. The third one, that says that C causes them both, so it's going to rule that out. And the fourth one, it's not just an accidental correlation if A causes B. So if you do that manipulation, you can find out that it really is the first case that holds, at least if all the other conditions are met. Now, you can also do it the other way around. If you manipulate B and A changes, but you manipulate A and B doesn't change, then you know that B causes A. But you also know that A does not cause B, because if it did, then when you manipulated A, B would change. And you know that it's not just some third cause, and you know that it's not just accidental. So now you've isolated the second condition as the one that holds if when you manipulate B, A changes, but when you manipulate A, B doesn't change. Again, this only holds when certain circumstances are in place. And I'm not going to go into detail and spell out what those are, but this is the basic idea behind a lot of experiments in science. Here's an example. Long time ago, they discovered that smoking correlated with lung cancer. And that led a lot of people to say that smoking causes lung cancer. But just imagine that you're a manufacturer of cigarettes. What are you going to do? Well, they were pretty inventive. They said, it's not the smoking that causes the lung cancer. It's the lung cancer that causes the smoking. Because when people have certain types of incipient lung cancer, that is lung cancer that's about to develop into full-blown lung cancer, it makes them want to smoke. It creates a discomfort in their lungs that's relieved by the smoking. And that explains why people who smoke more have more lung cancer. So we think that A causes B, the smoking causes the lung cancer. They're claiming that B causes A, the lung cancer causes the smoking. How do you tell? Well, you can't look at the temporal relation because the smoking is going on at the same time when the lung cancer is developing. So you got to do a manipulation. You set it up in a lab. You take a bunch of animals, in this case it was monkeys, who don't have lung cancer. You check them first, and then you force them to smoke. You put a cigarette in their mouth so that when they're breathing, they're smoking. And sure enough, they developed a lot of lung cancer. No surprise there. Poor animals. And that showed that it was lung cancer that was caused by smoking instead of causing smoking. Why? Because we didn't manipulate the lung cancer. It didn't affect the smoking, but we manipulated the smoking, and that affected the lung cancer, and that shows that it was the smoking that caused the lung cancer. Here's another example, which was kind of a mystery for a while. An economist friend of mine told me about this. Turns out that back in the 1960s, there was a positive correlation between having a television in the home and performance in school. Students were more successful in school if they had a television in their house. Some people actually claimed that television was making them better students. But in the 90s, it was the other way around. In the 90s, kids who had televisions in their home did not do as well on average as kids who had no televisions in their home. So there was a negative correlation. So how could there be a positive correlation between television and school success in the 1960s, but a negative correlation between television and school success in the 1990s? In order to decide between those hypotheses, you can't manipulate it. You can't go back and change the rate at which they're watching television and change their school performance and so on. You need to have some background information about the societies of the time and the kind of people who had televisions. Well, back in the 1960s, it was largely the more affluent, higher socioeconomic status people who had televisions because they were quite expensive and not that common. And those people typically are correlated with high school success anyway. High socioeconomic status and high school success have been correlated. And so it's that correlation that's explaining why in the 1960s, the students who had televisions in their homes did better in school. But in the 1990s, things had turned around. Parents were worried about their children watching too much television. And some parents actually kept televisions out of the home so that their kids would read more. They had more books and less television. And those kids were doing better in school. No surprise there. So in the 1990s, there were a lot of people who kept the televisions out. That produced greater school performance. And so you got different correlations in different times. And the only way to tell what was causing what was by looking at the background circumstances and knowing something about the societies in which these effects are occurring.